Hi, welcome back to College Algebra. Today we're going to be looking at real zeros of polynomials. So we're going to go and find answers to polynomials, and that's going to be kind of fun. So we're going to do a couple of tools, figure out a couple of tools here that we can use to help us along the way. So I'm going to give you those tools first, and then later on we'll just kind of summarize it all and put it all together so that we can find the zeros. So let's get started. The first thing we have is called the rational zeros theorem. So you can feel free to look this up. If you're using a textbook, it's absolutely going to be hiding in there somewhere. But basically what it says is if there are rational zeros, so anything that could be written as a fraction of a polynomial, they're going to take a certain form. And that form that they're going to take is fractions, p over q, where p is a divisor of the constant term, a sub 0 at the end of the polynomial, and q is a divisor of a sub n, the leading coefficient of the polynomial. And so all we're going to learn to do here with this is just to build these potential zeros. Now these won't all be zeros, thank goodness. I mean, there would be tons if they were all zeros. But some of them will be, and that's just going to be one of the tools that we have to try and find the solutions here. So you'll see I have an example. I have p of x is equal to 4x to the fifth minus 3x cubed plus 7x plus 6. So all I do for this is I'm going to list the divisors for p, the number at the end, the 6, and for that I have plus or minus 1, 2, 3, and 6. And I'm going to list the divisors for q, the 4 at the beginning, plus or minus 1, 2, and 4. And then all I have to do is put them all together to make fractions. Now my list might look a little bit empty, like there maybe should be a few other things, but I promise they're all there. So let's take a look. I have 1 over 1, which is 1. I have a half and a quarter. Notice they all have plus or minuses. That's legal. You could have positive or negative zeros here. Then I have 2 over 1, but I left out 2 over 2 because that's just another name for 1, and 2 out of 4 because that's another name for a half, which are already on my list. So then I have 3 over 1, which is just 3. 3 halves and 3 quarters, and then when I get to 6, I get 6, but again 6 over 2 is 3, and 6 over 4 reduces down to 3 halves, so I don't need those on my list. And that's it. So this is a list of potential nice zeros, and I know some of you are like, wait a second, 3 quarters? That's not a nice zero. Yeah, trust me, it could be a lot worse, and we'll see that. But so that's our potential zeros, and that's our first tool, the rational zeros theorem. So we're just using it to make these potential fractions that could work. All right, let's move on and look at our next tool. Okay, here is our second helpful tool as we go about trying to find real zeros for polynomials. It's called Descartes' rule of signs. You might recognize the name Descartes. He's much more famous really as a philosopher. He's the person who said, I think, therefore I am. You can feel free to go look him up. He's pretty cool. But anyway, so Descartes' rule of signs is going to tell us how many positive and negative zeros there can be. And again, it's going to give us possibilities, just like the rational zeros theorem gave us possible fractions that would work. So what Descartes' rule of signs basically says, and again, I'm really condensing it here so I can fit it on my board, but what it basically says is that the number of positive zeros is equal to the number of sign changes, or you can count down by 2 from there. And we'll see an example. The number of negative zeros is the number of sign changes in p of the opposite of x, so that's going to be a little bit different. Or again, count down by 2. So let's do an example. Here's my polynomial, 4x to the fifth minus 7x to the fourth plus 3x cubed plus 2x squared minus 7x plus 1. So all I'm doing is looking for places where it switches from positive coefficient to a negative or the other way around. So I go from positive 4 to negative 7, that's one sign change, and you can see I wrote that down there, 1. From negative 7 to 3 makes the second one. 3 to 2, nothing changes there, so I don't count that one. But from 2 to negative 7, that's a third, and negative 7 to 1, that's a fourth. So this one has 4 sign changes. We're just looking for those coefficients as we go down the list in order to change from positive to negative or negative to positive. So the number of positive zeros here could be 4, but then that second part of that was that you can count down by 2s. So I go from 4 to 2 to 0, so there are either 4 positive zeros, 2 positive zeros, or there aren't any. And any of those 3 things could actually be the case. We don't keep going because you can't have a negative number of zeros. That wouldn't make any sense, right? We're just counting up how many zeros there are. And so then for the negative zeros, now I have to plug in negative x. So I take my original polynomial and I plug in negative x in place of all the x's. Now, I didn't write that out because I was a little short on space, but all that's going to happen is anytime you have an odd coefficient, when you plug in a negative x, you'll keep the negative and it's going to change the sign of your coefficient. So this 4 went to a negative 4. Anytime you have an even coefficient, even power though, when you raise a negative to an even power, the negative disappears. And so nothing changes for the even power terms. So I kept my negative 7x to the 4th. Again, odd power, so I changed the sign. Even power, I kept the sign. Odd power, I changed the sign. And 1 is just 1. It doesn't have any x's there. You can't plug a negative x in and do anything with that. So again, I count my sign changes. This time I only have 1 from negative 3x cubed to positive 2x to the second power. So the number of negative zeros I have here has to be 1. So from this we can tell, what is possible with positive and negative zeros. We're going to combine that here in just a minute with the rational zeros theorem and our calculators to actually go try and find the zeros. So let's get a new board. All right, so now we're ready to start finding zeros. I have the steps that I think are really useful here laid out. And then on the next board, we'll actually get an example because, quite frankly, this little bit of space down here is not going to be anywhere near enough. All right, so finding zeros. First of all, how many are there? There will always be the same as the highest power of the polynomial, every single time. And that's something we'll look at again in section, I want to say 6. 2, positive and negative zeros. That's where we're going to use Descartes. How many are there? How many positives? How many negatives? 3, what are your possibilities? That's the rational zeros theorem. So now this is where we're going to bring our calculator into play. We're going to take our list of potential zeros and we're going to graph the polynomial on our calculator and we're going to compare the graph and the list to try and find zeros that we think work. Once we choose a zero that we think works, we're going to use synthetic division. If you get 0 at the end, you know you found a 0. And you have just shrunk your polynomial by 1 degree, which is great. If you don't get 0 at the end, you just have to try again. But once you shrink that polynomial, which we'll see, we're going to use that reduced polynomial to repeat steps 3 through 5. So back to the rational zeros in your calculator in synthetic division. Basically what we're going to do is we're going to take big polynomials and we're going to start shrinking them down till we get to a quadratic, and then we can just use the quadratic formula. So let's get an example on the board and we'll go ahead and do that. All right, so I have one example for you here. It's really hard to do really big polynomials because I have such little space. But anyway, here we go. P of x is 3x cubed plus 11x squared minus 6x minus 8. I know there are 3 zeros because that's my highest power. I know that for the positive zeros, there's only 1 because there's only 1 sign change from the 11 to the negative 6. If I plug in negative x, again, I'm going to change the signs of the odd power, so I get negative 3x cubed plus 11x squared plus 6x minus 8. And that has 2 sign changes from negative 3 to 11, and then from 6 to negative 8. So there can be either 2 or 0 negative zeros. So then I'm going to build my potential fractions, right, using the rational zeros theorem. The divisors of 8 are 1, 2, 4, and 8 with their plus or minuses. The divisors of 3 are just 1 and 3. And so you can see my massive list of potential zeros. Now, I don't want to have to go searching through all of that. So what did I do? I put it into my calculator and I looked at the graph. And I'm just going to compare my graph to this list of numbers. And if you do that, and I highly encourage you to do it, it really looks like 1 is a 0. So I'm going to try the synthetic division with 1. So I do the synthetic division with 1. I drop down the 3. 1 times 3 is 3. Add and I get 14. Multiply, I get 14. Add, I get 8. Multiply, I get 8. Add and I get 0. And so I go, okay, great. I got 0 all the way over here at the end. That means that I know that 1 is a 0. Furthermore, that means that x minus 1 is a factor of my original polynomial. So the original polynomial now can be written as x minus 1 times this quadratic. At this point, I threw it into the quadratic formula, or you could try and factor it. It does actually factor. But either way, And when I did that, I got x is negative 2/3 and x is equal to negative 4. So I have my 3 zeros. That's what I was looking for. And that's really all we're doing here. So there you go. That's finding zeros. It's going to be a fun process. Good luck.